Hey, it's Ko from Graz University of Technology, and in today's tutorial I would like to talk about vector network analyzers. The target audience is more on the beginner side, and we will cover 3 topics. First, I would like to talk about calibration, so the essential step in order to correct systematic errors, in particular phase and magnitude errors. Second, we will characterize a 100 nanofarad capacitor and build a model out of it. And at the end, I would like to talk a little bit about time domain reflectometry. In short, TDR. This is what you can see here already in the background. The very first step I'm doing here is to press here on the preset button. So this preset button brought back our device to its default setup. And our VNA has here 4 ports with so-called 3.5 millimeters connectors. And it's compatible with SMA, but uses air as dielectrica instead of Teflon. And we could now start to plug in our SMA cables directly to our port 1, but instead I would like to protect our port, our connector here, and thus plug in our through connector here to our port 1. And you always wheel here, where it's intended to wheel, and not on the device itself. Before we calibrate our VNA, we need to set up all the options first. And all the VNAs have very similar options, and we start by selecting the start and stop frequency. So let's say we start our measurement at 100 kilohertz and we stop at, let's say, 10 gigahertz. Then we can set the power level, so the power level our signal generator of our VNA is applying. Now it's set to minus 10 dBm, we can increase it to 0 dBm, and as you can see, the dynamic range increased slightly. Then we should take a look into the sweep options, where we can change the sweep time for a logarithmic sweep. We can increase the number of points to 5001, which means that at each decade we would have 1000 measuring points. This will result in a sweep time of roughly 1 second. Every VNA has somewhere a calibration option, and we can now start to calibrate our device. But first I would like to check whether the calibration kit I'm using is already stored in the device. So we can switch into this Cal Devices tab and take a look here into the Cal Kits. And the calibration kit I'm intended to use is already stored in my device. We can take a look into the standards and find here a definition for the load, open, short, and for the through connector. You can find it for different genders, male and female type. Let's take a look into the female open connector. So in addition to our open circuit here, we also have defined here a parasitic stray capacitance that changes with frequency linearly, quadratic, and by the factor of 3. Furthermore, we have a loss factor defined here and the delay factor that depends on the length of the open here. And we can check this for each connector, so also for the short connector. So the short connector has here, instead of the parasitic capacitance, a parasitic inductance defined. And the 50 ohms load is defined here ideally. So there will be no reflections and all the power will be converted into heat energy here. And now we can start with the calibration here by going on Start Calibration. It offers us different options, but let's start with the simple OSM calibration for open, short, and match. First, we need to select the correct connector, so it's a 3.5 millimeters connector. The gender of our connector here, not the gender of our calibration kit, that we select here. And then we can start the calibration. Okay, let's overwrite. And we start with the open connector, and here we can also check port 1 has a male connector and the calibration kits have female connectors. And we start with the open calibration, and you can see here that we have 0 decibels because all the energy that's coming to our open connector gets reflected back. And then we repeat this process for the short calibration. And here with the short calibration, we again see 0 decibels because also with a short connection all the energy gets reflected back, but there is a 180 degrees phase shift. And here for the load calibration, we can see here a broadband attenuation for about 40 decibels or 30 decibels here in the worst case. So most energy that's transmitted from the signal generator will be converted into heat energy inside our load. And then we finish our calibration by clicking here on apply. And since we did the one port calibration, we are only interested into S11, and it's hard to see, but it's a very good match. So we are here directly at the matching point. And now the so-called calibration plane is exactly here where the dielectricum starts or ends. For very low frequencies, we are here at the open point, and the higher the frequency gets, at 10 GHz, we have a phase shift here. This 100 nanofarad capacitor, I started it here on the SMA connector, and I can now plug in the connector with the component directly here. And again, for low frequencies, we are now starting here. In an ideal case, going down to 0 Hz, the capacitor would start here at the open point, and then it will make a circle here. Then here at 100 kHz, it's here. And here around 13 MHz, where it crosses the horizontal line, where the imaginary part is equal to 0, we have our series resonance point. And then the frequency increases up to another resonance point, this time a parallel resonance around 6 GHz. Of course, you can also change the format, for example, displaying the magnitude here in dB scale. And here we have to change the scale to have a better overview of what's happening here. You could also go here on measurement and switch to the Z parameters. And now we have here ohms on the y-axis, on the x-axis the frequency, and then you will find your series resonance frequency here. This is here. If you go on markers, you can also make searching markers, searching for the minima, and we're here at around 10 MHz. So we can go back here to format and switch from linear back to decibel scale. Then again, I will just adapt the scaling a little bit. And so it looks more like the capacitor as you know it from the text box. So you may have noticed that our calibration plane is still here. So in addition to our capacitor, we have additional trace length due to our SMA connector. Let me explain to you with the Smith chart. So if we unplug our capacitor now, and if we now mount an SMA connector without capacitor on it, and then you will recognize that the connector by itself causes a significant phase shift. And you can now correct this offset with an option that you can find in the calibration tab, but on this device there is a special button for it, the offset button. And you can now play around here with the delay. So by increasing the delay, you can see that the Smith chart goes here back to the open point. So this additional trace length causes a delay of our signal from approximately 35 picoseconds. But we can also try here this auto length button, and then it will give us 34 picoseconds. In addition to this phase correction, we can also correct the error in magnitude caused by our SMA connector here. For this, we click here on fixture compensation and then select port 1 that we would like to correct, and then it asks us either to have an open or a short. And in our case, we have an open here, correct the length and the losses, then click on start. And then in addition to our delay, it also introduced here a factor for correcting the amplitude here. Now let's back to our measurement. We unplug our SMA connector, and we should now see again a line, but this time counterclockwise. And now we will plug in our capacitor mounted on our SMA connector, and this time the phase should be correct. And now the Smith chart gives us a slightly different result, especially at the higher frequency regime. And now switch back to the Z parameters. And now the impedance over frequency looks like this, with the resonance frequency shifted to higher values. So if we now activate a second marker here, performing a search for the minima value, we'll find our marker somewhere here around 16.5 MHz, which means by correcting the phase error caused by the SMA connector, our resonance frequency is now shifted by about 7 MHz. Now let's store our trace here for later using this flash drive here. On this device you can save your data on file, trace data, and then let's export it as a touchstone file, the data of port 1. Then we can select the path. Let's take our flash drive, give it a name, and then this output format is perhaps also interesting, so you can switch between 3 options here and then just press on save. Okay, this is now the S-parameter file from our vector network analyzer, and we can see here in the so-called header that in the first column we have stored the frequency in hertz, so here in the first column, and then we have stored S-parameters in the format of real and imaginary part. So the second column contains the real part of S11, and the third column includes the imaginary part of S11. And all the measurements were done in a 50 ohm system. And we can now check this here in the Python script. So the first thing I'm doing here in Python is I'm loading this file, but I'm skipping the first 7 rows. So the imports should start here at row 8. And then I just have to assign the columns correctly, can calculate the S parameters or the impedance parameters, and then I'm just plotting the file. So just hit on the run button, and we have successfully imported the measured data. And we can check it also here. Let's check if the variable is correct. And here the first row contains the same frequency as here, and the real part and the imaginary part is also imported correctly. Now we can build an RLC model. So actually what's happening here is I'm adding R plus j omega L plus 1 over j omega C, and I can just select some numbers here, and then we're just plotting the data here on the same plot. So let's see what happens. And now I see the orange trace is not fitting the blue trace, because here in the low frequency range, the capacitance is too large. So the first step is that we have to select the correct value here. So let's go back to 100 nanofarads and then run the simulation again. And then we can see here the low frequency range, now it's fitting quite good. And for the high frequency range, the L is dominant, so we can play around and check what happens if I increase L and double the value. Then we can see that the resonance frequency shifted lower values, and in addition to that, here on the high frequency range, the impedance increased. So let's going back to 1 nanohenry, and we can also check what happens if I increase the resistance value. And in this case, we have more damping. At resonance frequency, we can then see here 1 ohms. Now let's compare our measured data with the data from datasheet. So here with the Red Expert tool, I can check the components from Würth Elektronik. So the datasheet gives a resonance frequency of approximately 16 MHz with an ESR of 27 milliohms. And if we check these values with our measured one, and so we can prove a good agreement between the datasheet and our measurements.